Good evening to all. Am I audible?
Yes, you are.
Good evening and warm welcome to everyone joining us today. Good evening and warm welcome to everyone joining us today. I am Rashmi Pant from the Department of Electronics and Communication Engineering, Mahaka Institute of Technology, Ujjain. It is indeed an honor and privilege to extend a warm welcome to all of you to the AICT ATAL sponsored online 6-day faculty development program 202526 on the topic Advanced Antenna Design for Next Generation Wireless Communication System 5G and 6G with AI Perspectives. We are truly delighted to have with us an eminent panel of distinguished guests and experts. Though we may be miles apart, this virtual platform brings us together to share knowledge, exchange ideas, and grow collectively, demonstrating the true power of digital learning. Before we proceed further, I would like to take a moment to extend A heartfelt welcome to our distinguished dignitaries who have joined us today. Engineer Shri Aditya Vashish Sir, Secretary Prasar Shikshan Evam Seva Sansthan, Ujjain, and also Vice Chairman of MIT Group of Institutes, Ujjain. Respected Shri Akash Vashish Sir, Vice Chairman, MIT Group of Institutes, Ujjain. Respected Dr. Mukesh Shukla Sir, Director, Mahakal Institute of Technology, Ujjain. Respected Dr. V.M. Shah Sir, Director, Mahakal Institute of Technology and Management, Ujjain. Respected Dr. S.C. Mahajan Sir, Director, Mahakal Institute of Pharmaceutical Sciences. Respected Dr. Rishi Dubey Sir, Director, Mahakal Institute of Management, Ujjain. Respected Dr. Vikas Jain Sir, Director, Mahakal Institute of Pharmaceutical Studies, Ujjain. Respected Dr. K.V. Sharma Sir, Dean Administration of MIT Group of Institutes, Ujjain. Dr. Abhishek Raghuvanshi Sir, Dean Academics, MIT, Ujjain. Respected Dr. Saurabh Gaur Sir, Head of the Department, Electronics and Communication Engineering Department, Ujjain. Respected Dr. Leeladhar Malviya Sir, Professor, SGS ITS, Ujjain. We are especially honored to have with us our esteemed chief guest, Dr. Dharmendra Singh Sir, Director IIIT Vadodara, whose gracious presence adds immense value and inspiration to this occasion. I also take this opportunity to warmly welcome all the faculty members and participants from various institutions across the country who have joined us virtually. Your enthusiastic participation is what makes this event truly meaningful and impactful. We are also pleased to acknowledge the presence of the event coordinator, Dr. Mohit Pant, from the Department of Electronics and Communication Engineering, MIT Ujjain, whose dedicated efforts have been instrumental in organizing today's program. In Indian tradition, every auspicious event begins with the lighting of the lamp, symbolizing the knowledge, wisdom, and positivity. Since we are meeting virtually, let us light the lamp in our hearts and begin the session with a spirit of learning and growth. To honor this tradition, we will now play a brief clip of the lamp lighting ceremony, accompanied by the melodious strains of Saraswati Vandana. हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ. हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ. तू स्वर की देवी है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे. तू स्वर की देवी है, संगीत तुझसे, हर शब्द तेरा है, हर गीत तुझसे. हम हैं अकेले, हम हैं अधूरे, तेरी शरण हम, हमें प्यार दे माँ. हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ. मुनियों ने समझे, गुनियों ने जानी, वेदों की भाषा, पुराणों की वाणी. हम भी तो समझे, हम भी तो जाने, विद्या का हमको भी अधिकार दे माँ. हे शारदे माँ, हे शारदे माँ, अज्ञानता से हमें तार दे माँ. Now, to formally commence the session, I now invite Dr. Mohit Pant, coordinator of this faculty development program, to kindly give us brief overview of the program.
Am I audible?
Yes, sir, audible.
Respected Chief Guest, Dr. Dharmendra Singh Sir, Honorable Secretary Sri Aditya Vashish Sir, respected Director Sir Dr. Mukesh Shukla Sir, Dean Administration Dr. K.V. Sharma Sir, Dean Academic Dr. Abhishek Raghuvanshi Sir, our HOD, Electronics and Communication Department Dr. Saurabh Gaur Sir, eminent speakers, faculty members, my supervisor Dr. Liladhar Malviya Sir, Professor, SGITS Indore, and all the participants and the research scholars who are connected today. Namaskar and very good evening to all of you. It's my great pleasure to welcome you all to the ATAL Online FDP program, 6-day online program on advanced antenna design for next generation wireless communication system 5G, 6G with AI perspectives. This FDP is initiative by the AICT ATAL Training and Learning Program, which aims to empower faculty members across the countries with knowledge and skills in the emerging technology such as artificial intelligence, machine learning, Internet of Things, next generation communication, 5G, 6G, cloud computing, cybersecurity, and many others. As you all know, many of our faculty members did not get chance to learn this topic during our BTech or MTech program, as these technology are quite new and rapidly evolving. This FDP is a great opportunity for participants to refresh and enhance their knowledge in this important and emerging technology. At MIT, we have believed that academic institutions must serve as active contributor to national development. We support the government of India, Skill India, Startup India, and ATAL FDP. MIT works hard to follow this program to make a difference in engineering education. We are proud to host this FDP as part of that commitment, bringing today top experts, researchers, and educators to share their knowledge and build capacity in one of the most vital area of technology today, next generation wireless communication, 5G and 6G powered by AI. As we look toward a future driven by 5G and 6G technology, antenna systems are evolving into highly intelligent, adaptive, and efficient component of communication infrastructure. Today, covered in this topic will include advanced antenna design for 5G, 6G, simulation using CST and Taran, meta-surface, massive MIMO and beamforming, integration of AI, ML in antenna development. We are honored to have eminent speakers from premier institutions like IIT, triple IITs, international universities, and reputed industries who will guide us through this exciting journey over the next 6 days. I also want to add that this FDP cover over 18 different state and union territory participants across the India. This remarkable diversity truly reflects the wide acceptance and importance in this program. We have total of 269 participants from all over the countries. These participants lies from the various regions, various states including Tamil Nadu, Madhya Pradesh, Andhra Pradesh, Maharashtra, Gujarat, Karnataka, Delhi, Odisha, West Bengal, Jharkhand, and many more. Before I conclude, I would like to extend my heartfelt thanks to today's speaker and chief guest, Dharmendra Singh sir, who also taught me AI when I have attended the QIP program at Triple IT Vadodara. And I feel very blessed that my two teachers are there. One is Dr. Dharmendra Singh sir, and other is Dr. Liladhar Malviya sir, Professor GSITS Indore, who guide me a lot during my PhD. Thank you to all. Now I am handing the session to Dr. Rashmi Pant for further proceeding.
Thank you very much, sir, for outlining the objectives and structure of the FDP. Now, to take the program forward, I invite the head of the department, Professor Saurabh Gaur sir, ECE Department, MIT Ujjain, to overview about the department. Over to you, sir.
Thank you, madam. Am I audible?
Yes, sir.
Okay, thank you. Sa vidya ya vimuktai. Knowledge alone is true, which free us from all bondage. With these words of Vishnu Puran, I, Dr. Saurabh Gaur, on the behalf of Department of Electronics and Communication Engineering, Mahakal Institute of Technology, Ujjain, welcome you all to the inaugural ceremony of this AICT ATAL FDP. Mahakal Institute of Technology Ujjain was founded in 2001, approved by AICT New Delhi, and is affiliated with RGPV Bhopal. In the last 25 years, MIT has become a center of academic excellence in the Central India. MIT Group offers courses in engineering, management, pharmacy, and computer applications. Department of Electronics and Communication Engineering was also established in 2001. It offers BTech and Master of Engineering in Electronics and Communication. The department focuses on both core and emerging areas such as antenna design, image processing, artificial intelligence, and Internet of Things. On this occasion, I congratulate our coordinators, Dr. Mohit Pant and Dr. Rashmi Pant. Their vision, hard work, and dedication have made this FDP possible. By bringing together expert and participant, they have given a great boost to the academic spirit of our department and our institute. This FDP is a symbol of spirit of effort, research, and innovation. Nahi gyanen sadrisham pavitrami vidyate. In this word, nothing is as pure as knowledge. With these words of Srimad Bhagavad Gita, I give my best wishes to the coordinators, all the resource persons, and participants for the grand success of this FDP. Thank you. Over to you, Dr. Pant.
Thank you, sir, for your
My,
insightful and encouraging words.
my special request is that I am Professor Dharmendra. Okay, once the people are talking, please on your videos also. No? So, hello.
Thank you, sir.
Yeah. Just a small suggestion that once anybody is talking, so please on your video also. So it will look hybrid, virtual plus real. So this okay.
Thank you, sir, for your kind suggestion. Now, I take this opportunity to invite our esteemed Dean Administration, Dr. K.V. Sharma, sir, to kindly address the gathering. Over to you, sir.
Very good evening, all of you. On behalf of MIT Group of Institute, I welcome our respected Chief Guest, Dr. Dharmendra Singh, Director, Triple IT Vadodara, esteemed resource persons, faculty members, and dear participants. It is great pleasure to me to welcome you all in this ATAL sponsored 6 days online faculty development program sponsored by AICTE based on advanced antenna design for next generation wireless communication system 5G, 6G with artificial intelligence perspectives. This FDP is a significant step in empowering faculty members, research scholars, and students with the latest knowledge and tool to the emerging and disruptive technologies. Under the initiative of the AICT Training and Learning Academy, ATAL, this program is designed to bridge the gap between traditional teaching practices and the rapidly evolving demands of the technological world like artificial intelligence. To all the participants, this is a great opportunity to learn, unlearn, and relearn to the technologies. I encourage you to actively engage in this session, interact with the experts, and take back insight that can enrich your teaching and research practice. Once again, I welcome all the participants, guests, esteemed resource persons in this online FDP program. Thank you. Thank you, Rashmi.
Thank you, sir, for your kind and motivating address. Now, I would like to invite Dean of Academics, Dr. Abhishek Raghuvanshi sir, to kindly address the gathering. Over to you, sir. Now, sorry, Dr. Abhishek Raghuvanshi sir, Dean Academics, MIT Ujjain.
I think he's busy somewhere. Please call to the next guest.
Okay, thank you, sir. Now we proceed further. I would like to invite Dr. Leeladhar Malviya sir, Professor SGSITS Indore, for few words.
Good evening, everyone. Am I audible?
Yes, sir.
Okay. First of all, I congratulate Mr. Mohit Pant and Rashmi Pant for organizing such an FDP. And I want to say namaskar and charan spars to my mentor, Professor Dharmen Singh sir. Good evening, sir.
Good evening, Malvi
Ji, sir. How are you, sir?
Very fine. I am very happy to see, hear your voice and all other things. That's great.
Thank you so much, sir. Thank you so much. And I also appreciate the efforts of Mr. Mohit Pant and the Rashmi Pant, and I congratulate them for such an great course, and also wish them to organize such courses in the future. I also thank all the participants who have joined today and the management of the MIT College. Thank you so much.
Thank you, sir. Before requesting our distinguished guest to share his thoughts, I would like to take a moment to briefly introduce Dr. Dharmendra Singh sir, Director IIIT Vadodara. Dr. Singh is a senior member of IEEE and highly respected academician with more than 30 years of experience in teaching and research. He completed his PhD in electronics engineering from IIT Varanasi and has received numerous prestigious fellowships from countries like Japan, Germany, France, China, and Brazil. He has guided 38 PhD scholars, published over 350 research papers, and led more than 40 sponsored research and consultancy projects. His key research areas include artificial intelligence, computer vision, machine learning, microwave imaging, stealth technology, and satellite-based application. Dr. Singh has been recognized nationally and internationally for his innovative contributions. He received the National Gold Award for e-governance 2 years in a row, the Best Innovation Award at India Mobile Congress, and has been ranked among the top 2% scientists in the world by Stanford University. Previously, he served as senior professor at IIT Roorkee and held several leadership positions, including head of the Department of Computer Science and Engineering. He is also coordinator of Drone Research Center, RailTel IIT Roorkee Center of Excellence in Telecom and Common Research Technology Development Hub, IIT Roorkee. It is now my privilege to welcome and invite our distinguished chief guest, Dr. Dharmendra Singh sir, Director IIIT Vadodara, to address the audience. Sir, we are truly honored to have you with us today. May I now request you to kindly address the gathering.
Thank you, Dr. Pant. Thank you. And nowadays, name is more than sufficient. Everybody is there. Okay, thanks for your briefing and all. And thanks a lot to the Dr. Mohit, because he knows that I am too much busy, but he caught me. And that's a very good spirit. And Mohit, I would love that you can go forward with this spirit.
Thank you,
You
sir.
have to catch, then you have to catch it.
Thank you, sir.
You have to do, then you have to do it.
It's truly our
Either I am replying or not replying or whatever is the things. So that's great. And so therefore, first of all, thanks to the Mohit. And therefore, I am here today. And I would love that if I can give such type of lecture in offline, but due to the time constraint, not possible for all to this one. This type of nowadays, and another very interesting thing today, just I came to know that Mohit is the student of one of my very favorite student of IIT Roorkee, Dr. Malvi. And so now Mohit is just like a grandson.
Thank you, sir.
So
It's
that
privilege, sir.
means nobody can imagine for a teacher, for a
Sir,
professor.
I am
If-
interrupting you, sir.
Yeah.
Today, Mohit and Rashmi both got the official award of the PhD
Oh,
letter.
great. Badai ho. That's
Thank
great.
you, sir.
So
Thank you,
very
sir.
auspicious day for both, and congrats to both. And for any teacher or any professor, nothing better than this. His student is doing very well, and his student of a student is getting some good degree under his supervision. So nothing better than this. And I think that today this is a very auspicious day for me. Regarding the course, nowadays for all participants, now it is it was the personal one, but for all participants, my request is that nowadays the information is flooding. Everybody, they know that YouTube or online or ChatGPT is going to solve maximum problem, or they are knowing that they can know it. But as per my personal experience, since last 30 years teaching from abroad to the India and abroad, both places, and that nothing can be replaced by the class teaching or this type of lecture. So it is my personal request and advice to all, whoever is going to take the classes or whoever is going to give the lecture, you have to listen very carefully, because this is the course for the faculty development. This is not the course just for any BTech or anything, something like that. Then you don't know the people how they are thinking the out of box. No, you can't imagine. I travel more than 20 countries just to understand what I am thinking, it is correct or not correct. If you will see my profile, more than 50 PhD students and a lot of projects and some products also. I have started a startup also. I am not saying that this is the very big achievement or whatever be the thing, but I was traveling everywhere. I used to discuss when Dr. Mohit was here for the QIP program. I have delivered one lecture also. So just to understand what are the need, how to handle that need in a different way, and how to think in a out of box. These type of courses is not meant only for to teach you or to make understandable what is the antenna or what are the courses or what are the things, what is AIML, whatever is the thing. Infinite informations are available and maybe you are knowing that thing. But what is the difference? How you can make the difference? That is the most important thing. That only you can be able to understand by the experience of the person. No chat GPT, no any online resources can give that one. Very simple thing I am saying that. In India, in RF domain, 40% researchers are doing the antenna design, fabrication, these, that, whatever be the things. But if you will go and see the Amazon, not a single antenna we are selling. In a technology, research paper is the byproduct. In a technology, the main is your product. Research paper is the byproduct in the technology. So how you are going to sell the antenna, how you are going to sell your product, that is the most important thing. If you will see that in Europe, Maximum people, they are just publishing paper in conference, this here and there, and they are much more concentrated to develop the product. So, and now once we are talking about the Atmanirbhar Bharat, we are seeing that whatever be the geospatial, nowadays geospatial drama is going on, a lot of geospatial drama is going on, and where we are seeing that everybody is talking about Atmanirbhar Bharat, Viksit Bharat, 2047, developed country. All the dreams only come true when we are trying to develop the product. Therefore, if you will see the, if you are applying for any project and all other things, the funding agency is asking the TRL, what is your technology readiness level? 3, 4, 5, 6, 7, 8, how to transform it. So that is a very important. I think that this course is very, very important. And you know, I heard somewhere 3, 4 days before I was listening something. So now in online platform, nobody can teach you. Nobody can teach the teachers. It is impossible. This is my personal view. Nobody can teach the teachers. So only what we can do, we can put a torch on your hand. Okay, this is the torch. Now the path is yours. So we are just putting a torch. We are trying to put the torch in your hand. Okay, now the path is yours. Make your path. So India become Atmanirbhar. India become, Bharat become Viksit Bharat. Bharat become the Vishwaguru, whatever be the dream for all of us. So with this word, because the next talk is mine only, with this word, I would again like to thanks to all the organizers and again request to all the participants to be patiently listen every speakers. All the nowadays, just last line I will let you know, because for all the professors, all the teachers nowadays a big challenge how to ask the student to sit in the class. That is the biggest challenge we are facing, bigger than the border challenge. How we can ask the student to sit in the class, and if they are sitting, you have to give the guarantee to they are listening you, because it is again very big challenge. They are sitting in the class, but they are not listening to you. So in this scenario, our role is very, very important. What the difference we have to make in the class, what the difference we have to teach them, so they can try to understand, or they can try to listen you in the class. So with these words, once again, all the best and best wishes to the organizers. And I hope that this 5-day ATAL faculty development program will be fruitful and helpful to all. And I would suggest also that some small groups you can make, try to have some take challenge and design some antenna or some part of things, and that would be one of the best part of that one. So once the Mohit group was here for this QIP, I heard that several students, they have published a very good papers in a conference and all by doing the course for the QIP. So this type of activity is not only the listening or learning, it should have some tangential output also, except the learning and all. With these words, once again, thanks a lot to the Dr. Mohit. And he caught me and he forced me, sir, मैं छोड़ नहीं सकता. That's a very good idea, very good things. All the best, and hopefully you will be enjoying the coming days for listening different lectures. Thank you very much. Jai Hind. Over to Dr. Rashmi.
Thank you very much, sir, for the thoughtful words of appreciation and gratitude. Before we proceed to the much awaited expert lecture, let us take a moment to express our heartfelt gratitude to all the dignitaries and speakers who have graced the inaugural session with their presence and words of wisdom. I now invite Dr. Mohit Pant to deliver the vote of thanks for the inaugural session.
Namaskar and good evening to all of you. On the behalf of MIT Group of Institutes and Department of Electronics and Communication and the organizing committee, it is my privilege to extend a heartfelt vote of thanks to all of those who made this FDP success. First of all, I want to thank our esteemed chief guest, Dr. Dharmendra Singh, sir, for gracing this occasion with his presence and support. Sir, we look forward to opportunity of welcoming you physically at our institute and listening to you face to face. Second, I want to thank my supervisor, my mentor, Dr. Liladhar Malviya sir, for his constant support and motivation. After that, I want to thank our visionary Vice Chairman sir, Sri Adhish Vasisht sir, whose encouragement and always motivated attitude pursue this academic excellence. Our respected Director sir, Dr. Mukesh Shukla sir, Dr. K.V. Sharma sir, for his leadership and constant support. And our HOD, Dr. Saurabh Ghosh sir, who always motivated us to organize such FDP. And my thanks to all the senior professors and faculties and staff members who organize and help this FDP. Now I invite Dr. Dharmendra Singh sir for his expert lecture. Dr. Dharmendra Singh sir, over to you.
Thank you, Dr. Mohit. I am sharing the slide. Is it visible?
Yes, sir.
दिख रहा है?
Yes.
Yes, sir. It is visible.
So talk will be in English, Hindi and English both. So because
Many of the participants are from South region from.
yeah. So but I will talk English doesn't mean that Hindi.
Okay.
English is understandable to all.
Okay, sir. No problem.
Yes. So that I have seen that
Yeah.
a lot of the participants from the south.
Yeah.
So today when Mohit has requested to give a talk on the antenna and for the advancement of antenna design, 5G, 6G, AI, role of AI, whatever be the blah. So first, very important thing, what I am going to discuss today in 1 hour or 45 minutes, first 45 minutes, after 30 years of teaching, what I felt that what is the missing. So that part I will first discuss. As I have mentioned that nobody can teach the teachers. So I will discuss. I used to say that discuss the things. Maybe you are knowing or maybe it will be refreshing. Because for any design of antenna or any system design, we must have to understand what is the basic principle, what is the philosophy behind it, and what is the current need. So if I say the 5G or 6G is a very over enthusiastic. We are thinking about that, but still we are somewhere in 4G and not in the all 5G and all other things. But once we are thinking for the 4G, 5G or 5G, 6G or wireless network. So if I say the wireless network, the only one point which we want, the seamless connectivity, nothing more than that. So the key point is that the seamless connectivity by any means, either you are designing a very good system with a very good SNR value, or you are designing a very good antenna, or whatever be the things. There are a number of things are there. But at the end of the day, we want a seamless connectivity. So generally, I used to ask in the class, because it is not a class, once we are trying to purchase a mobile, what the important features we are trying to see that. One or two, maybe one or two person can give the answer. What the important features we are expecting from the mobile? If we are going to buy a good mobile, anybody can say, because just giving a blind lecture, that is a very tough. So just one or two person can reply. Just for first also 2 minutes, and after that. So if I say that we have to purchase or we have to buy a good mobile, what would we like to see in that mobile? Anybody?
Good evening, sir.
Yeah.
Yes, this is Pramod from Hyderabad.
Yes, Pramod. Yes. Again.
Yes,
Great.
sir.
Yes, tell me.
Yes, sir. In general, in general, we are using mobile. So for speed up the system, how it is effectively working.
Yes. Go ahead.
And
speed of the system means what we have to see. For example, somebody wants to say that you have to buy a mobile. I want to buy a mobile. What the specification do you want to see?
RAM,
yes.
And operating system for security mechanism purpose.
Oh yes, security, yes. Anything else?
And these things, sir, I think I am observing.
Yeah. Anybody else?
Sir, processor is also very important part, sir.
Good afternoon, sir. This is Vinita.
Yeah.
Hello.
Yeah. Please go ahead, Vinita. Yeah. Tell me.
Well, it depends.
Hello. You are not audible. You are not audible, please. You are not audible, Vinita. You are not audible.
Sir, good evening, sir.
Yeah.
Sir, this is Rajnikant from Andhra Pradesh.
Yeah. Yes.
When we see mobile, we'll see camera resolution, RAM, ROM, then
RAM.
multi-band operations Bluetooth, Wi-Fi, internet.
Yeah.
Then screen resolution. So usually we see all these parameters. Of course, cost.
Yes. Huh? Cost effective. Yes. That's good. Yeah. Cost effective. Yeah. Anybody else?
Yes, good evening, sir.
Yeah, please.
Sir, handiness of the mobile is also very important aspect.
Handiness, yes.
How much, along with that, processor?
Yes, already mentioned, RAM mentioned, processor mentioned.
Yeah, and size of screen display system is also, sir.
Yeah, display system, yes.
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 Sir, am I audible now?
Yeah. One more bus only. Yes. Tell me, yeah. Yeah, please.
Sir, actually, while we are purchasing any mobile, it depends upon their own perspective in which type. So, for some extent, some people need the portability, some people need the security system. But overall, once anyone purchasing the mobile, the first and foremost thing they will see how much battery percentage it can be survived. And second thing, the portability, that is less actually, and the security level, that what extent they can have. So most of the people are allowed to have the iPhone actually because of its feature of security, which we not having much in the Android. But still some companies are making their own mobiles like very secure, but the Mac is the first one which we ever beat till now
Yes, sir.
actually.
Okay, thank you.
So okay,
Thank you. Yeah. Thank you very much. Thanks, yeah, just okay. That's good. I got all the points. Can you tell all of you, whoever is listening, whatever somebody had mentioned, speed of the system, RAM, OS, operating system, security, camera, ROM, multi-band objective, screen resolution, cost effective, handiness, display, battery, security, all these things. In all these features, any feature is related to the connectivity, because the first thing I have mentioned that the mobile device must have the seamless connectivity. Whatever be the features you have mentioned, or I have read just what I have written all the features and what you have mentioned. Any feature is giving the connectivity information. Anybody? Anybody? Just tell Vinita or the Pramod or Rajnikant. Anybody? I am means na. I means I am a board teacher. I used to teach in the board on the board, but okay, online is okay. Without seeing the people how to teach, that is a very tough job for a teacher. Yes, tell me. Therefore, I ask that. Anything in that, whatever be the features someone mentioned, it is any connectivity related thing, features are there?
sir,
No,
you're stating
no,
that
sir.
the wireless communication, that what we are stating now,
Yeah,
that's what you're
wireless
stating, sir.
communication, mobile
Yeah,
communication. So for communication purpose, any connectivity feature is there?
No, sir. 5G or 6G not is there.
Yeah.
So connectivity, what we want for connectivity?
We need the signals
What
to
the
be
features?
strengthening, sir.
Bandwidth you
Strengthen
wanted, no, sir?
Huh?
standard.
Bandwidth, sir.
Yeah, we
No,
need
what
the
is
frequency where the mobile need to operate
no, it is
and
okay.
how.
Frequency is
Okay,
okay.
sir.
But one more point, very important point is missing. That is not
Sir, is
mentioned
it
in mobile. Metro mobile, it is not mentioned. They are hiding because they are making us fool. Because first important thing for any mobile is the connectivity to get the good connection.
Yeah, sir. Signal strength with the
antenna, sir?
less
What
noise
is
ratio.
that? What is the signal strength? What is that? You are
So the
50% correct. You are 50% correct. Signal strength.
signal strength with the less noise ratio. So when it comes to when you are
Yeah.
designing an antenna, we will thought about the scattering parameters like the return loss and transmission losses.
No. Don't go in that. Don't go in
Okay.
that.
Okay.
So don't go in that. Don't go in that. That is the SNR, signal to noise ratio.
Okay.
So I am giving you one assignment to all of you. Just try to search the signal to noise ratio of the Apple phone, Samsung phone, Vodafone, Oppo phone, OnePlus, this, that. So then you will be able to understand if two persons are standing at a same place. For example, two persons are standing at Ujjain. It's the same college, Mahakal College. And one person is having the mobile phone of Apple and another person is having the mobile phone of OnePlus. Service provider is same, Airtel. But what you will be observed in Apple phone or in OnePlus, in one phone your signal strength is more and in another phone the signal strength is less. So the most important thing which no company is mentioning in their data sheet, that is the SNR value. That is the most important thing, because I am not going to tell today. You have to write to the Mohit and Mohit will compile it and then it will be sent. This is the most important thing. Once you are going to buy a mobile, you have to see that what is the SNR, minus 140 dB or minus 160 dB or minus 180 dB. Therefore, if somewhere, I don't know. Now, earlier, once we are complaining to the service provider, for example, Airtel, oh, I am at Mahakal Institute, but I am not getting any signal here. So he used to ask nowadays with the MAC ID, they are able to understand which mobile you are using. But 4 years before, they used to ask which mobile you are using. No, sir. VI will not work. You have to use the OnePlus or something like that, or some upgraded mobile. So SNR is one of the most important thing for the connectivity. Therefore, I have mentioned that what I am going to discuss, that maybe a lot of people you are maybe knowing, but the most important thing, what is the things required to work with the AI, and then after that it depends how the different people are dealing with this one. So first 10-20 slides will be what is the basics of the antenna. If I say about IIIT Baroda, you can see that this is one of the very interesting figure. Anybody can say what the interesting thing you are seeing here? Anybody? Just to make it fun.
Electromagnetic radiation, sir.
I mean, EM waves.
Huh?
Electromagnetic radiation.
Anything else? Radiation can be like this one also. Radiation like this one. This is also like radiation by rays. What the difference you are seeing?
Radiation pattern.
No.
Radiation.
What the difference you are seeing?
No, bidirectional it is radiating, sir.
Anything else? Or kuch?
Waves, sir, waves.
Waves. Or anything? Are you seeing what I have drawn?
Yes, sir.
Omnidirectional antenna.
No. Are you seeing that what I have drawn with the red color? It is visible or not?
Yes, visible, sir.
Those are
Yeah.
signal waves.
Please listen very carefully. So we can show the radiation by putting like this one. We can show the radiation by putting like this one. But what the difference? Here we are seeing the radiating by making the loops. ये loop बना रहा है. It is making the loops, and that loop is propagating. It is not a simple wave. That loops, you are seeing that loops. You are observing the loops. Huh? You are seeing the loops. So another very interesting thing which I am going to discuss, when this loop will detach, then therefore once we are talking the antenna, we are talking the three things: near field, between the near and far field, and the far field. If I say near field, what does it mean? Near field, what does it mean? Near field simply means
distance. It is a distance.
The distance, okay. Everybody put the near is near. That is square by lambda. Anything else? Anything else? Anything else?
And this is the area where electromagnetic waves detach from the antenna.
No, not near field. It is not detached. So, what is the near field? If I say near field, yes. What the first bell rings in your mind?
Near field, the radiation pattern will be dependent on the distance.
Yes, it is the second line, first line. Yeah, very good. Radiation pattern.
And the near field depends on the dimension of the antenna.
Yes, very perfect. Anything else?
In near field, generally we will store the energy of how much of energy stored in that region.
Yes, very good. Excellent. Yes. Anything else? So, in a more layman language, how we can say that? What is that? If I say visualize the Shiva's third eyes. Electromagnetic is just like a Shiva third eye. Shiva only can see the waves. So once we are teaching in electromagnetic, if you are visualizing what the things are going on, then you will enjoy like anything. So if I say visualize the near field, what will you say? Visualize the near field. What will you say? What will you visualize?
Oscillation, sir.
Oscillation. Very good. Excellent. So in near field, it is non-propagating, non-radiating. In near field, it is oscillating. Oscillating means just blinking, just like a star blinking. 0, 1, 0, 1, 0, 1, 0, 1. It is just like a blinking. And it is oscillating. When it will be oscillating means what it should have? It should have L and C, inductive and capacitive, because we know that the oscillation F is equal to 1 by 2 pi under root LC. So it is known as the non-reactive field. It is known as the non-radiating field. So, and here it is L and C are more dominant. So and once we are saying near field, it is meant it is oscillating, it is just like a blinking. And if I say the far field, it is a radiating field. And what he has mentioned, what one has mentioned, then it will not depend, the radiation pattern will not depend on the distance and whatever be the things, other things. So once we are talking the antenna, so we are saying that the antenna is transducer because changing the energy, wave to energy, energy to wave. And I will discuss the region of transition, as I mentioned, that from when it will, if I say the antenna, what are the, when I say, please off your mic because there's some noise is there. If I say antenna, please off your mic because some noise is there. If I say किसी के बच्चे की आवाज आ रही है, please off your. If I say that what are the two important points once we are designing an antenna? What is that? S11 is minus 10 dB or whatever is that thing, except that, what is the two important thing? Hello? Anybody? What are the two important points once we are designing an antenna?
Wavelength and frequency, sir.
Huh?
Wavelength and frequency.
Yeah, that depends upon what antenna we are designing. And for designing an antenna, their shape,
return loss and gain also is different.
Return loss, yes. Return loss where? Return loss where?
At the time where the antenna should provide maximum gain.
Return loss where? So there are two important points in an antenna.
Gain and directivity, sir.
No. There are two important points once we are designing. That is the important parameter. Just listen. There are two important points. One is the feed point and another one is the mouth of the antenna. So feed point, what is the important thing for the feed point? What we are observing? The feed point, the impedance should be approximately, feed point, impedance should be approximately, once we are talking, the S11 should be less than minus 10 dB. So if once we are talking at the feed point, what would be the impedance here?
50 ohm.
50 ohm.
50 ohm.
50 ohm. Very good.
50 ohm.
So one is the 50 ohm. So because we are knowing that whatever be the cables we are connecting here, then maximum energy will be transferred once impedance will be matched. Second important thing, what would be the impedance at the mouth of the antenna?
377 ohms.
377 ohm, 125 or 377 ohm. Then energy will be transferred to the atmosphere or air. So these two very important things. So once we are saying the transducer, how the waves are converting to the energy, waves are converting to the energy means field. It means we are transmitting mode or receiving mode. We are in receiving mode. And once the electric field is converting to the energy, is converting to the waves, then will be the transmitting mode. So I will discuss. So that is the things. So one thing is very important here. Once I have mentioned the impedance. So I have mentioned till now 3 words. One is the near field, far field, radiating, non-radiating, oscillating. Near field oscillating means the reactive. So when energy will be transferred, maximum energy will be transferred when impedance will be matched. What does it mean? When it will transfer? It will transfer because we know the impedance is equal to, we know that impedance is equal to Z is equal to R plus JX. So when maximum energy will be transferred, when maximum power will be transferred, when
Load impedance will be matched.
Load impedance will match. What does it mean?
Matched to source impedance.
When
Means
JX becomes 0, when only real part is there. When only real part is there. So R is very important. So therefore we are knowing that R is resistance. So therefore this is the equivalent circuit. If you will see that, this is the transmitting mode and the transmitting, and this is the transmitting antenna and electromagnetic wave. If I say the antenna is propagating a wave, what kind of wave it is? What kind of wave it is? What kind of antenna is propagating a spherical wave? So there are 2 things very important. So spherical, therefore, once we are talking the 5G, MIMO, this, that, we have to understand that what important thing we are going to design for a maximum gain, maximum spatial diversity, maximum time complexity, for the maximum the direction of arrival, or whatever with the things. Beamforming, all these things are coming from the very basic. So once you can see that this is the transmitter. Sorry, this is the transmitter, transmitting antenna, and this is the receiving antenna, and this is the spherical wave. And therefore antenna is propagating in a radial in all directions. And the different type of antenna, we are knowing that is the different type of antenna for the dipole antenna, monopole antenna, Yagiuda antenna, helical antenna, whatever we now, the this antenna, patch antenna, whatever be the things. So this is the very important slide, that when energy will transmit. So what should be the equivalent circuit for that? So here the transmitter will be, we are knowing that is the one generator will be there, and once the generator is there, generator impedance will be there. And here at antenna point, that is the impedance, that is the R equivalent plus JXQ, which I have mentioned that. And it will be maximum. Therefore, what we are trying to do today, I will little bit discuss about that. We are trying to reduce this one, and we are trying to increase this one to get approximately 377 ohm at the mouth. Therefore, once we are talking the body-centered antenna. So body-centered antenna means, are the antenna immersed in any liquid? If antenna immersed in any liquid, then their nearby environment, the impedance will be changed. So that impedance is required at the mouth of the antenna. It is not necessary that it is for the free space the 377 ohm required. Otherwise, that impedance is not required for this antenna. Similarly, when it is the receiving mode, then what would be it? Then what would be it? It would be equivalent to the Z, that is the voltage, and the equivalent impedance, and here the load, where the whole potential V we can measure that one. So these are the two very important things. What would be the antenna equivalent circuit when it is the transmitting or receiving mode, and where we are going to play it. So what we are saying, so you can see that. So this is the impedance real part. So we are much more interested to make our antenna by changing the shape, by changing any means. So resonance occurs when the capacitance and inductance vanishes. What does it mean? What does it mean? In a simple wire, if it is a dipole, simple dipole, we are saying we have the L and C both here. What does it mean? We are saying that if E and H field, E H, how we can correlate the E and H field with the capacitive and inductive behavior? Anybody? How we can correlate the E and H field with the capacitive and inductive behavior? So we are saying that if E is leading with H, then it will be the capacitive. And when E is lagging with the H, then it will be the inductive. And E and H both are in same phase, then it will be the pure resistive. So here once we are saying that this is the resonance, resonance simply means here our E and H both are. Therefore, we are taking the dipole as a lambda by 2. Today I have not so much time, then I will otherwise discuss why it is lambda by 2. So E and H are in both phase. So we are saying that E and H are both phase, then the resistance impedance will be the pure resistive. Then only the energy will be transferred. Can you imagine how you define the far field? We are saying that the far field is 2D square by lambda. What does it mean? What does it mean? Anybody? Far field. Far field. We are saying that far field is 2D square by lambda. What does it physically mean? Anybody? Am I audible or not?
Sir, it covers
Hello?
180-degree radiation pathway.
No. What does it mean?
It is the distance where the spherical wavefront can be
It is
converted to plane
it is a
wavefront.
very simple. Yeah, it is a distance where the therefore we are radiating. What does this technically physical meaning? I am sharing my IP is what I have learned. So that is the thing. A lot of things. It is written in the book only. I have not written any book, or I have not written any concept. I have read more than 1,000 times, so I can get these points. And today I have mentioned that the first few slides, what I am trying to discuss, that what I have felt that in the class, that something is missing, and it is. So what do you mean by how you can define it? I have mentioned that the far field will start where the energy power will transfer. When power will transfer? When the impedance become the purely resistive. When impedance will be the purely resistive, when E and H both are in the same phase. So at the far field point, at the 2D square by lambda, it is observed that E and H becomes pure in a same phase. And if E and H becomes in a same phase, then at that time it is a pure resistive and the energy will transfer. And then from there the radiation will start. So that is the very important aspect for that. So once we are designing the 5G or 6G antenna or any G antenna, 4G, 2G, 3G, whatever be the G. So that is a very important thing once we are talking, because nowadays we are very much dependent on the simulation software. But software does not know what we are trying to do. The software cannot read our mind. We have to teach them. We have to teach the software. No, I want this one, you have to do this. So already I have mentioned that this is the transmitting mode. So we have this one in the transmitting mode, and if it is a receiving mode, so we have but natural at the receiver end, this is the load where we have measuring the voltage and all other things. So we are knowing that if I say what is the special characteristic for any body or any structure where we can say, for example, wire, I am talking about wire, where we can say that it will be radiating. When it will start to radiate? Anybody? When it will start to radiate?
When its length is lambda by 4.
Lambda by 4 or lambda by 2, yes. Anything else? I am not asking why, because I will discuss later on, kabhi mauka mila to, because that I can only discuss on the board or something like that. I cannot discuss all these things in the slides and all other things. Anything else?
The movement of the carriers in the antenna, either accelerating or decelerating of the current, then
Yes,
it is
perfect. The movement means the most important thing is that if the electron, whatever be the traveling in the antenna, they are accelerating or deaccelerating. Just 1 minute. Just 1 minute. Battery. Huh? Hello. Hello.
Yes, sir.
Yes.
Yeah.
So the most important thing is the acceleration or deacceleration. So only then it will be then only it will be the radiating, otherwise it will be not radiating. And another very important thing, in the mouth, we are making such, so its impedance become approximately 377 ohm or something like that. So I will discuss this. You can see that this is a simple plate, and therefore generally we used to ask if it is a simple waveguide, it is radiating or not radiating. Simple waveguide is radiating or not radiating? Anybody? Simple waveguide is radiating or not radiating?
I think so. It's not radiating, sir.
Why?
Just it is a medium, na, sir.
No, medium doesn't matter. Every guide is medium only. Doesn't matter. We are making with the waveguide, same waveguide, we are making the flaring we are doing, the horn antenna, we are making this simple flaring, then it is radiating. It is not radiating. Simply because here the impedance of the mouth is very, very less than the 377. And we are making the flare such that its impedance becomes 377. So therefore a simple waveguide is not radiating. So you can see that I will show you how it is making the this one. How it is making the loop, and how it is making, how when it will be disconnecting with the antenna. So there are three important points. If there is not moving any current, is zero, no radiation. Charge is moving with any uniform velocity, then also no radiation because there is no acceleration or deceleration. If charge is accelerated or deaccelerated, only then the radiation will occur. So for example, you can see that if it is a curved surface, bent surface, discontinuity, or the terminated, something like that, so then the antenna will radiate. So this is the transition for the different, as I have mentioned in the first slide, that is the guided wave. This is the transition region of antenna. All these things are related to their impedance only. Okay, how we are making it, and in free space it is making a loop. I will show you one simulation for that one. And then if this loop is a spherical wave, this loop is propagating, which I have shown in the second slide. So I am not going to detail, just you can see that what is happening. This is the Hertzian dipole. If it is at t is equal to 0, then at t is equal to t by 8, then at the maximum t is equal to t by 4, at that time resistance will be maxima, and this will be detached from the antenna. This is the beauty. Then once the cycle will reverse, then again it is 3 by 8. Therefore you can see that 3 by 8. Then again, and at that time, whatever be the things are here, at that time this loop will be traveled by the distance lambda by 2. So how once it is going from one cycle to another cycle, then it is moving by the loop. So this is one of the most important point. How, so people are asking, okay, charges are attached with the antenna, when it will detach.
Please repeat, sir.
Charges, you can see that. Yeah, it is this figure is from the Balanis. You can read the Balanis.
Yes,
I am just giving you this one. So I am not going to detail of this one. You can see that at t is equal to 0, the E field is something like, sorry, E field is a plus to minus. It is a plus, it is minus. At I is equal to 0. At t is equal to t by 8, so field becomes like this one. And once T is equal to T by 4, when I is equal to maxima, I maxima will when I max will be maxima when the resistance, it will be the pure resistive, and it will be, once it will be the pure resistive, then it will detach from the antenna, because resistance only the with the heating, with the other things, it is dissipating the energy. And similarly, once the cycle will reverse, then 3t by 8, and once it is a t by 2, this loop will be traveled by the distance lambda by 2. So this is the whole process when it will be detaching and when it will be, how it is moving to the forward direction. So, and this is the impedance, how, as I have mentioned, that this is the most important thing, the impedance on the mouth. And we are not, I have shown you that this is the ZA is equal to RA plus at the input impedance of the, and I have mentioned there are two impedances, one at the feed point and one at the mouth of the antenna. What I am talking here, it is at the mouth of the antenna. Feed point is approximately 50 ohm. At the mouth of the antenna, by tapering or by changing the shape of the antenna, we are changing the impedance of the antenna. So the total resistance RA will be the RR plus RL. So all these things are there. And I have what I have shown you, this is the transmitting antenna, and then at the transmitting antenna, the equivalent is this one. RR radiation resistance, XA, and this is the RL is the RR is the radiation resistance, RL is the loss resistance, XA is the inductive and capacitive part. Similarly, for the receiving antenna, we have RR, and this will act as a generator, and it will act as a this one as a load. So we are getting the receiving antenna for that one. And similarly, you can see that all the equivalent circuit, the Norton equivalent, Thevenin equivalent, we can make as a, on the basis of equivalent circuit, we can define what would be the this one. And then why I am discussing here, all these things are very important point. On the basis of that, we have to design the antenna. What is the power delivered to the antenna? What is the power dissipated as heat in the generator? Radiated power? Because all these things, if I say the pattern of the antenna, what do you mean by that? Pattern of the antenna, antenna pattern, what do you mean by that? If I say this is the pattern of the antenna, what does it mean? Anybody? What does it mean? Anybody?
Lobes, sir.
No, lobes to hai, dikh raha hai. This is the, now we are not, this is the lobes, yes. Anything else? Pattern of the antenna, radiation pattern of the antenna.
It is the spatial distribution, sir,
A spatial distribution of what?
of electromagnetic wave.
Of power or electric field? Or much more physical explanation?
Power, sir.
It can be power or electric field, sir. We can draw a field pattern as well as the power pattern.
Yeah, power pattern or the field pattern. Yes, perfect. What does it mean? One more level lower?
Normalization, sir.
Huh?
Normalization.
No. It is okay. Either it is saying the power pattern or the field pattern. It is okay. One more line down to understand what is happening. What is that?
At each angle of theta and phi, what is the power at that angle?
Yes, very close. It means if we have 1 watt, transmitting 1 watt, whole 1 watt is distributing in this. For example, if it is a 1 watt and it is like something like that, so we can say that here it is 0.8 watt, it is 0.15 watt, and it is 0.05 watt. Just 1 minute. Just 1 minute. But hello. 5 मिनट, 5 to 6 मिनट अभी बस एक मीटिंग में मैं 5 मिनट अरे किसी का एक्सीडेंट हो गया. Yes, no problem. So if I say hello, am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
मैं अभी उठाया तो मैसेज दिया है. हाँ, just a minute. So, just 1 minute. So if I say that it is a 1 watt, then 0.8 watt is here, or 0.7 watt is here, 0.2 watt is here, and so all the power is distributed like this one. So what we are trying to make, that the maximum power should be in the main lobe and rest it should be very small. That is our job for once we are designing an antenna. If I say the 5G or 6G antenna, what does it click? क्या क्लिक करता है दिमाग में? What does it click?
Some frequency. They contain
if
the
I say
higher
antenna,
frequency.
if I say antenna, that is frequency bandwidth. Anything else? What does it click? What the new concept it is saying?
Connectivity
So
for
beam
all.
forming is also the concept of 5G and 6G related.
What?
So beam forming.
Beam forming.
Beam
Anything
forming.
else? Anything else?
Facing, sir.
No, beam forming, phasing, the same thing. Anything
Yes,
else? Beam forming is okay. Anything else? Beam forming. Have you seen that any image? If 5G, 6G, if I say any new concept came in the picture, that is the massive MIMO or MIMO.
So it's
MIMO?
massive MIMO.
Massive MIMO. MIMO or the massive MIMO. So just you can read. So massive MIMO or MIMO means we have to be very spatial diversity, very good spatial diversity and all other things. So MIMO means one channel is talking with the one channel. So if I say the MIMO, so simply MIMO means there are 3-4 antennas and all antennas are radiating in a different direction. So for one channel, one antenna is talking, another channel, another antenna, another part is talking, third channel, third talking. So there, till now, what is happening? Only one channel is there and all are talking with this. So with that, if MIMO, if we can do like that, so then time it will enhance the connectivity and it will reduce the latency also. So all these things, therefore, the power management is one of the most important things. So I am not going to discuss the details of whatever be at the receiving part. We must have to know, because all the game is with the SNR. If I say we have to calculate the SNR, which formula we are using? Which formula we are using to calculate the SNR? For the wireless communication, for power measurement or for power, which formula we are measuring? By which we are anybody? That is known as the Frisch equation. That is a very important. Just you can note down and you can read it. The Frisch equation. So by using that, and then you can see that Frisch equation, antenna is one of the part. And rest, another part is also there. The power, this, that, distance, a lot of things are 3-4 parameters are there. So what we have to improve? We have to improve the SNR value. So for improving the SNR value, therefore everybody is talking about the antenna, how good antenna you can design, so we can improve the SNR value, and then our connectivity as well as the latency should be reduced. So I am not going to discuss, just you can read it, the infinitesimal. Here what I want to say that, which I have mentioned that already, at the antenna is propagating a spherical wave, and it becomes a plane wave at a once the electric field and the magnetic field are in phase. So at a far field distance, it behaves like a plane wave, and therefore we are measuring the plane wave on the mouth of the antenna. So, and there are two concepts. If it is a spherical wave, and if it is a very far, and then the distance of this and the distance of this becomes negligible. This change will be negligible to this change, and then the spherical waves becomes the parallel wave. So, and we are, for any antenna, we are receiving the parallel wave. So I am not going to, I have just little bit mentioned about the radiation pattern, and I will come to your AI part. And another very interesting, important thing. 99% people, very bluntly I am saying, they are measuring the antenna gain in a very, very wrong way. So there are a ratio method, just you can note down, there are a ratio method. This is the one of the best method to measure the antenna gain. So where we are putting the reference. What do you mean by reference antenna? What do you mean by reference antenna?
Standard antenna.
Standard means where the gain is known. For example, we are transmitting a frequency at 1 gigahertz. At 1 gigahertz, its gain is 5 dBi. It is known. So how much power it is receiving at that point, at that frequency, and then we are replacing our DUT, actual antenna. So how much power it is receiving. So we are knowing if this much power is received by the known antenna, and this will be the unknown antenna multiplied by the gain of the known antenna. And by that, we are calculating the gain of the unknown antenna. So this is a very important thing. Please note down the ratio method. Just search and read it, because a lot of people are using the Frisch equation to solve the gain, because Frisch equation is very much dependent on the distance. If you are measuring the distance, a small error is there, then your gain will be changed a lot. So ratio method is one of the best method to measure the gain. So just you can read down for that one. If I say the classification of antenna, so we are saying that the wire type antenna and the aperture type antenna. What does it mean? Wire type, how we have classified it? Wire type antenna and the aperture type antenna. So what we have, what is the measurable quantity? Measurable quantity, we have either the current or the field. So once we are knowing what is the equivalent current on the mouth, then we can calculate at any distance what would be the power. Or once we are knowing the equivalent field on the mouth, then what would be the equivalent, what would be the power at any distance we can calculate. So on the basis of that, we are classifying. If it is a wire antenna, we are talking in terms of the current. In the aperture antenna, we are talking in terms of the electric field. So, and so that is the different class of antenna. So this is the wire antenna. The different antenna we are knowing. This is the aperture antenna, and now the patch antenna also. If I say that the patch antenna, what is the principle? What is the principle of radiating for the patch antenna? What is the principle for radiating the patch antenna? Anybody? If I say patch antenna, what is the principle? Am I audible or not? Hello?
Yes, sir.
Yes, sir. Yes, sir.
कुछ तो बोलो, नहीं तो समझ ही नहीं आता, लगता है अंधे के सामने बात कर रहे थे. It's very difficult to discuss all these things online, especially the EM theory or antenna. So if I say the patch antenna, what is the principle? One word. That is very important. That is?
So fringing fields.
Yes, good. That is the fringing field. So we have to know that how the leakage is there. Leakage is due to the fringing field. So that is the things. So in nutshell, this is the all about the antenna. The circuit quantity, antenna impedance, radiation resistance, antenna temperature, physical quantities, size, weight, current distribution, and then the space quantity, whatever we want. So once we are trying to understand, and once we are able to understand all these things in a very, very specific way, then we can design, we can try to design an antenna. We can. Otherwise, simulator is designing an antenna, just you are changing the length, the breadth, height, this, that, and it is giving some results. And we are not knowing, can publish some papers, but we are not able to sell the antenna and all of those things. So some practical consideration. So role of AI for antenna design, just 10 to 20 minutes. Everybody is knowing that. Types of AI, the reactive, limited memory, theory of mind. Another very interesting thing for AI. It is my personal advice and request. I am the pioneer of AI in India, means I am working in AI since last 1999, when it was known as the decision support system. So one thing is very important. Computers should not tell you whatever he wants, he will do it. You have to tell the computer, okay, I want this game, I want this feature, and then you have to do the analysis. Otherwise, now in all the CNN and all other things, what is happening? Just you are giving the output, you are giving the input something, it is giving some simulation and some results are coming. But we are using just like a black box. We are not knowing that how the current is going to change, what the parameter we have to change to. And now again, very important thing. I have more than 40-50 theses I have evaluated for the different universities and institutes. People have started to design an antenna. Okay, we have written and designed an antenna for 5G, 6G, for example. But they are not knowing the actual frequency, for what specification they are going to design. Anything is coming, they are not mentioning they are going to design for 6 gigahertz and minimum bandwidth required is 1 gigahertz. They are mentioning, okay, frequency is 6 gigahertz, but bandwidth is missing somewhere. So if they are getting 0.2 gigahertz bandwidth, or if they are getting 0.3 gigahertz bandwidth, doesn't matter. So it is not like that. You have to very specific for your objective. Then you can design an antenna. It used to take more than 1 year to design a simple antenna, according to your wish. According to computer wish, you can design every day one antenna. So reactive, limited memory, theory of mind, and self-awareness. Reactive, intelligence to perceive and react to the word in front of it. So just like this, you can see the chess, that is the reactive one. Limited memory, stored previous data, predictions when gathering information and weighing potential. So previous data for automotive car and all other things. Theory of mind, it is just theoretical, it is still in theoretical, not have not achieved the technological and scientific capability. So what is the robot, how do you think, how to take the decision, what to do, the special case, all these things are there. Self-awareness, the self-awareness is also, we are talking the reinforcement learning or all other things. So Real-time application, you can see that many real-time applications are there. People are using for the different aspect. Traditional versus AI design for the antenna. We are knowing that we have a software, we have a parametric sweep, we have a manual tuning and optimization, and how we can do the things with the AI. So automatic design iterations, learning inverse model, because these softwares are very, very expensive. And then people are trying to reduce the cost as well as some important thing using the AI according to their wish. But if I say the AI, the most important thing is the huge amount of the data set. So now what the people are doing, they are generating the synthetic data set using the different software, and then they are taking that one as a input, and they are trying to design their antenna as per their wish. Intelligent antenna system learning algorithm, we are knowing that. I am not going to discuss. Everybody knows that supervised, unsupervised, reinforced. And overall method is that AI, machine learning, then deep learning, and then the neural network, artificial neural network, whatever the things are there. Techniques, added design techniques. That is, as I have mentioned, that this is the inverse design geometry prediction. What is the inverse design? We can say that we want this gain, we want this frequency, we want the slot antenna. Then automatically it can give the dimensions and shape and size of the antenna. So that is one of the way. Second one, and for that purpose, we are using the deep neural network, variational auto encoders. Forward modeling, we are having the antenna design, shape, and all other things. And then we can optimize that. What is the requirement? So, and there we are using the CNN, feed-forward neural networks. Optimization, as I have mentioned that there are two words, optimal and optimization. So optimization, maximizing the gain, minimizing return loss. So different tools like genetic algorithm, PSO we are using. And the surrogate modeling. So surrogate modeling means the both one. So train a fast surrogate model like neural network or GP. So ultimately aim is with a cost-effective solution and with a more precise engineer design, how we can achieve our aim. So you can see that inverse design. So all these things I have collected from some work we have done also in our lab, but that I am not showing because it is under the patent. It is under the patent. So but the inverse designing, as I mentioned, that we know we want that how much gain, what are the things are required, and then it is going to give the shape of the antenna. Forward modeling, already we are knowing that what are the dimensions and all other things, and what the gains are required. So we are just tuning this one, L1, L2, L3, L4, and then we are getting the things. Parametric tuning scenario, different parametrics tuning are there. Surrogate model, I have mentioned that is a mix of both one. And then we are getting that application of AI to antenna design, that you can see that this is the, and if we are saying the wireless, then a lot of things we have to use, the latency, gain, and the diversity, connectivity, SNR value, a lot of things. And so people are now, if you see the routers, they are having the 4 channels or 2 channels router. One is 5.2 gigahertz, another one is 2.4 gigahertz. One antenna is 900 megahertz. So whatever the channel is there, you can use it. That is the phased MIMO. So you can see that MIMO is something like this in a different direction, and now it is a beam forming. So in which direction, the direction of arrival is maxima, we can use that one. For people are using for the robotic also, okay, how to control all these things, radar signal processing and all other things. You can see that switch, once we are talking the 5G, 6G antenna, switch beam antenna and the adaptive array antenna. Just you can note down, these are two very important. Switch beam antenna is not adaptive. So it is by giving the different weights to the antenna, we are switching this one. And in adaptive antenna, automatically it is taking the weight and where is the direction, maximum direction, automatically it is changing that one. So re-engineering, as I have mentioned, that we are knowing the shape, we are knowing this radiation pattern and all, so we can have the things. So ML model, DL model, I am not going to today discuss. Sometimes there is no need to use the AI or ML machine learning. We have to know that at what condition machine learning is required and at what condition machine learning is not required, what kind of data, what kind of complexity we have. And there are three words: simple machine learning, shallow deep learning, and the deep learning. So where it is required, the deep learning, because now the era is coming for the edge computing. So people are trying to have all these things in a very, very shallow deep learning, all the less computation power. Antenna design challenges, as I have mentioned, that challenge is infinite. What I have shown you, the input, output, size of the antenna, shape of the antenna, gain of the antenna, efficiency of the antenna, and then if it is a 5G, 6G, then the spatial, temporal diversity of the antenna, all these things are there. So how we can deal with that, that is a very challenging task for that one. Future standardization and regulatory roadmap. So you can see that ITU 3G to 6G, where we are hoping in 2031 some 6G standards will be there. Till now we are somewhere here. 2025 we are facing this one. So conclusion that high cost implementation, we have to be very careful. Can't replace humans, no need to worry. Does not improve with experience. So as I have first line, I have mentioned that everybody's experience is very important once you are dealing that. And then lacks of creativity. So we should be very careful while using the chat GPT and all other things, because a lot of time what it is required, it is not giving the answer. So we should be very careful. And then the risk of unemployment is less. I am not going to worry for that. The takeaway thing is that strategic planning is not meant to be a storm within a program. So whatever be the program or whatever be the things you are using. So bibliography, several online, offline resources, something like that. Thanks for the patience. I used to say that without GEAL, you can't do anything. So you should have a GEAL for that one. Any queries or question, you can, one or two questions I can take. And otherwise you can share with the Mohit and he will give to me, then I will try to answer that. Thank you very much.
Any queries from the participant side? You can also write in the chat box.
Sir, no query, sir. We need a PPT, sir.
PPT, I never used to give PPT.
Sir, I have a question. What is the
Yes,
disadvantage of using AI in antenna design?
Yeah. What, please repeat.
So what is the disadvantage of using AI in antenna design?
No. Disadvantage is that because we do not have the enough data to train the model. So once, for example, if we do not have enough data to train the model, maybe after 4 or 5 years, it will be one of the best tools. But currently we have to develop the data. So that data is not available and we have a very limited data. With that limited, for example, whatever today I have discussed, everybody is knowing that thing. It is not that I am first time trying to discuss. But if it is not in your database, then whatever be the results or whatever the things you are going to get, it is not up to the mark. So that is the thing. So maybe after 4 or 5 years, it may be one of the best tools.
Okay, sir. Thank you.
Please guide the research concerned in this AI models.
Any other queries?
To
So
find out problem statement in this AI modeling of an antenna.
there is
Research.
a Mr. Zakir, there is a relation between the SNR and the SAR, specific absorption rate. And this is a well defined. Nowadays, all the mobiles, they are writing the SAR. What is the SAR? So it is not depending on SNR. It is basically depends upon how much power you are transmitting and receiving. So for any mobile, the transmitting may be the 2 watt and the receiving in somewhere milliwatt or something like that. So we have to be that. And therefore, the challenge is constant is the, otherwise, if you can make the transmitted power 10 watt, 20 watt, then but naturally your SNR will increase like anything. But constant is that you cannot transmit the microwave in a very high power microwave or something like that. Okay. So that is the thing. Okay. Anybody else? Otherwise, thank you very much for your time and all other things. Now,
Good evening, sir. Excuse me,
good
sir.
evening. Yeah.
Sir, actually, I want to know the data set. The
You have to generate the data set with the
how much,
CST.
sir? How much data set is required for to optimization of antenna?
Means if it is a, you can say that what kind of antenna. For example, if you are designing a patch antenna, their
Yes,
length
sir.
and breadth are and frequency and all things are there. Then you need some maximum, means the thousands of the data for the different dimension, different to this one. So how precise you are generating the data set, then that is important. Just 4, 5, 10 data is not going to work a lot.
Okay.
Okay. Okay, Mohit. Thank you very much.
And thank you, sir. I would like to sincerely thanks from the bottom of my heart,
Thank you, sir.
Dr. Dharmen Singh, sir, for their insight concept of the antenna and insight into the AI-based antenna. I believe that the participant will gain valuable knowledge from his session. Thank you, sir.
Okay, thank you, Mohit. Thank you all.
From the next time, we will hear you physically, sir,
Yes.
from face to face.
My just you can search my mail ID will be in net. Hina,
Okay,
Dr. Hina has mentioned that. Or Mohit will share the.
Okay, sure, sir. I will share, sir.
Okay. Okay. Thank you all the best. And as per my request, everybody must attend the lectures very seriously because whoever be the speaker, they are going to share their experience also. That is the one of the most important thing. Thank you very much. Okay.
Thank you, sir. Have a nice day, sir.
Thank you so much, sir.
Our next expert speaker for session 2 will be joined soon.
Dr. Mohit,
Yes, sir.
please provide 5 minutes break.
Okay, sir.
You can announce.
Okay, sir. We can take 5-minute break. Don't log out from the Google Meet. We will join after 5 minutes. Am I audible?
Yes.
Yes.
Yes, sir.
Yes, sir.
It's my honor to introduce our expert speaker of session 2, Dr. Jome Angure, IEEE Fellow, co-founder and CTO of Agnon, a leading technological company based in Barcelona, Spain. Dr. Jome is a renowned researcher and inventor with over 213 granted patents, many licensed globally, impacting more than 200 million devices. He is credited with pioneering the antenna booster technology, a breakthrough in wireless connectivity for IoT devices. With over 25 years of R&D experience, Dr. Jome has authored more than 300 scientific papers with 9,500 plus citation and H-index of 56, author of 8 books. He currently serves as a professor at Roman Lulu University and holds several editor and leadership roles within IEEE. His expertise and innovation have earned him multiple awards and global recognition in the field of antenna and wireless technology. Please join me in welcoming Dr. Jome. Over to you, sir.
Thank you, Dr. Mohit. It's a big pleasure to be with all of you. And thank you, the organization, and also to you, Mohit, for inviting me. So I'm going to share my screen. Please let me know if you can see it.
Yes, sir.
Can you see my screen?
Yes, sir, it's visible, sir.
Okay, so let's get started. In today's presentation, titled Antenna Booster Technology for Wireless Communication, we are going to understand a novel technology that is very unique for designing wireless devices embedding antennas. Let's for a moment put into the shoes of a microwave or wireless RF engineer dealing with amplifiers, filters, directional couplers when designing wireless devices. At the end, you don't need to know what's inside an amplifier or what's inside a filter. At the end, integrating all those components, what matters, for instance, for an amplifier is the gain of an amplifier, the input impedance, output impedance, the noise figure, and so on. But when it comes to the antenna, you have to be an expert because there are so many techniques, PIFA, IFA, slots. So you have to be an expert when you need to integrate those kind of antennas. So the question here is, can we do things in a different way? So can we treat the antenna as any other component, as an amplifier or as a filter? So at the end, we can use in our design in the same way. So that's the purpose of my talk today, to present this technology, antenna booster technology, to simplify the design of wireless devices. Here you have my email, the first one from the company and the other one from university. If you have any question, please use my email, any of those. So I will be glad to answer whenever I can. So the journey for today will be why we need this technology. We will understand the architecture. I will provide some physical insights, how this technology is useful to design wireless devices for single band, multi-band operation, for any kind of protocol, okay? 5G, Wi-Fi, Bluetooth. Also, we will compare this technology with other antenna technology. Also, if I have time, or at least a couple of minutes, I will like to connect this technology to green connectivity. And finally, conclusions. Also, I will share my presentation to Mohit with extra reference for any one of you if you want to deep dive and do more research in this topic. The scope or where we focus or where this technology shines is in the so-called wireless devices or Internet of Things.
As you know, there are hundreds, millions of devices that need to be connected into the cloud, so they need to send data in a very efficient way. And most of these devices, also, they are battery powered, so you cannot plug at the end of the day. So this means that the device, the connectivity, has to be very, very efficient. This means that the antenna itself has to provide a very efficient performance. And in which frequency range we are talking about? Mainly in the one that you can see in the screen. For the low frequency, about 0.4 gig up to 10.6 gig. Why is that? Because in this frequency range, we find all the cellular protocols, narrowband IoT, LTE, 4G, 5G, Bluetooth, Wi-Fi, ultra-wideband. So all these protocols is where this technology shines. And for kind of devices such as smart tracking devices, smart meters, sensors, and so on. Also, the market is huge. As you can see in this forecast, the number of connections by the year of 2030 is going to be around 30 billion connected devices. So this pushes universities, institutions, and companies to put a lot of focus in this IoT from the antenna perspective and from the electronics perspective, designing transceivers, amplifiers, and so on. Let's start with what is the typical antenna technology to design small and multi-band wireless devices such as mobile phones. So in this slide, I illustrate some of real examples of antennas integrated in the top or the bottom part of a mobile phone. As you can see, all these shapes are different, and these are the metallic parts of the antenna that we have to manipulate the geometry to make the antenna small and also multi-band. For instance, to operate at 800 megas, 900 megas, 1800 megas, 1900 megas, and more frequency. So that's the reason why we need to shape the geometry of the antenna. This is the so-called self-resonant antennas. So this means that the geometry of the antenna is in charge of providing the performance at the frequencies of operation. The question here is that, for instance, you can see that these mobile phones, they look more or less the same, and even they operate at the same frequency bands. However, no antenna is the same. So the question is, can we make something different? Can we make something new in such a way that we can use only one antenna component for any frequency band and for any form factor? So this is the very interesting question that we addressed a long time ago, by 2007, say, okay, what's typical in most of wireless devices? The ground plane. And the ground plane, which is populated of electronics, at least one of these layers in a PCB, it's a ground plane. It means it's a conductive element that can be used as an antenna. So what we said is, okay, instead of using a complex geometry to make the device operate at multi-band frequencies, why don't we use a small component able to excite currents on the ground plane, yet providing the same performance of these elements, but being smaller, simpler, and usable for any frequency band and any form factor. And this is what we did. We researched it, and I'm going to present the results. We call it this technology antenna booster, because this tiny component is electrically very small and provides boost currents on the ground plane. And from the commercial point of view, we founded a company in 2015 called Ujjain. And from the commercial point of view, we named this technology virtual antenna technology. However, in this presentation, I'm going to use the most technical name, the most scientific name used in papers and books, which is antenna booster technology. First patents that we submitted, the first appear in the literature, are about these antenna boosters to provide operation for single band and multi-band kind of applications. In here, I illustrate the overall evolution of antennas for wireless devices from the well-known external monopole, typically single band, quite large, about 100 millimeter, Then the first internal antenna appears by 1996. Still, you see the size of these antennas were big. And as the time went on, the volume of the antenna was reduced, but still you can see that they rely on shaping the conductive part of the antenna. The big breakthrough is with the apparition of antenna booster technology, which is based on this antenna booster component, 10 times more or less smaller. You can see perhaps in my finger. Let me show in the screen this tiny component that I have now in my fingers. In this case, it's only 5 by 5 by 5 millimeter to operate at cellular bands. Okay, and not only that, it's small, but it's also an off-the-shelf component that can be easily embedded into a PCB like any other component, like an amplifier or a filter. So in terms of mass production, this is very convenient. And the nature of this component is non-resonant, whereas these structures, they are based on resonance of the antenna. We will see that these elements, since they are electrically small, they are non-resonant. So the question is how we can provide performance being non-resonant. Let's find out in the following slides. Let me briefly show you which is the architecture of an antenna booster based system. It's very simple. On one hand, we have this component, the antenna booster, typically is lambda over 20, lambda over 30, so really very small. Then the second ingredient is the matching network between the antenna booster and the transceiver in charge of transmitting and receiving the information. And then the ground plane. The ground plane is the most important part to provide bandwidth and efficiency because its size is comparable to the wavelength. So by properly locating the antenna booster in the PCB, we can effectively excite currents and as a result to have a device that is efficient. So based on these three ingredients, the antenna booster, the matching network, and the ground plane, we can have devices embedding antenna boosters being 10 times smaller than self-resonant antennas. Let me put this metaphor, how the antenna booster work. As you may know, an acoustic drum, you have the drum stick and you have the membrane. So by properly pushing the membrane with a drum stick in the center of the membrane vibrates, and as a result, it creates sound waves. So it's not the drum stick which radiates, it's the membrane who perturbates air and creates the sound wave. Drum stick has not to be big, very big. At the end, it has to be of a certain length to push the membrane. And also what matters is the position. You can push in the middle of the membrane, then you will create sound wave. But if you push at the boundary of the drum, it's hardly to make sound wave because there is no vibration of the membrane. So it means that the position of the drum stick matters. So in the same way happens when we embed an antenna booster in a PCB with a ground plane. The antenna booster will be like the drum stick. The position of the antenna booster along the PCB matter to make the ground plane the in charge or the element in charge of creating the electromagnetic wave. Let me illustrate what is the difference when we design wireless devices embedding self-resonant antennas compared to antenna booster. Imagine that we need to provide operation at single band. This illustrates frequency. In blue, we have the S11, and in pink, we have efficiency. So by shaping the conductive part of the antenna, this is a monopole. The blue line is a monopole on a ground plane. So by shaping the geometry of the antenna, we can tune the antenna to have a good operation across a single band. Now, for the same device, if we need to add more bands, then we need to sophisticate the antenna design, perhaps by adding a new branch into the antenna. So this creates another resonance. You can see in blue, the S11, or in pink, the efficiency. So now we are changing the first design to a multi-band design. And also, we can expand the frequency band at the second region, perhaps by adding parasitic elements, so making the antenna bigger, sophisticating the antenna. So in this case, we are expanding the band. But overall, what I want to highlight is that depending if you want single band, dual band, or even more bands, the key here is how we design the antenna element. The antenna element has to be different. However, for antenna booster, this is totally different, totally on the other way, because we can have the same antenna booster, the same component, and by only changing a matching network, which in this case it's only inductors and capacitors, very tiny SMD components, we can go from single band by using, for instance, a two-component matching network to a, say, dual band or triple band response by adding 5 components in this case. And last, to increase the bandwidth in a certain bands, then we can sophisticate the matching network. And not only that, the beauty of this approach, which is more like a microwave problem, is that the design of the matching network can be totally addressed by software, by any microwave circuit simulator. So this is very simple to obtain the topology and the value of these components in the blink of an eye. Now let's talk about a big or a small device. When we say a device is big and when we say a device is small, and what are the issues of a small device. So overall, we can simplify these equations. And let me only focus on the last equation. When we say length represents the length of the device in comprising the ground plane and the antenna. So when the length of the maximum length of the device is less than lambda over pi, where lambda is the wavelength at the lowest frequency of operation, we can say that the device is small. And what happens if my wireless device is small at the frequency bands of operation? So let's have a look at it. And in this case, we have an antenna booster. In this case, it's only 12 millimeter and at the frequency of 900 megas. This represents an electrical size of the antenna booster of only lambda over 30, more or less. In blue, we have the ground plane. In this case, this ground plane is 120 millimeter length by 60 millimeter width. So let's imagine now that we take the same antenna booster, this red component here, and we change the length and width of the ground plane from a very small ground plane of only 20 by 20 millimeter to a large ground plane of 300 by 20 or 20 by 300, and also to 300 to 300. So in this matrix, we have many, many ground planes, and what we want to find out is the bandwidth we can obtain. We always use the same antenna booster, but the size of the overall structure depends on the size of the ground plane. So let's imagine that we simulate this structure. We simulate the S11, and with some particular equations, we can estimate the bandwidth we can get at the frequency of 900, for example. Let's see what happens. In this graph, we have in the horizontal axis the length L of the ground plane. And in the vertical axis, we have the width of the ground plane. So from 20 by 20 millimeter up to 300 to 300 millimeter. And the colors represent the bandwidth for a SWR equal to 3. So blue or dark blue represents 0%, yellow, green colors 20%, and red colors more than 35%. Let's see what 30 millimeter in length or width, the symmetrical situation. In terms of lambda, this means around 0.4 lambda. So as a result, if we want to maximize the performance of a wireless device when we embed an antenna booster, the size of that device should be about 0.4 lambda at the frequency of operation. In that case, we can have a huge bandwidth. For other sizes, you see that, well, bandwidth changes, it goes to a minimum, then a maximum, okay? But what matters now here is if we make the ground plane smaller and smaller and smaller and smaller. You can see that once we go from a, say, 0.4 lambda ground plane, and we make the ground plane smaller, the bandwidth is being reduced 5%, 2%, and so on. So this is one of the drawbacks when we integrate not only antenna booster, but any kind of even self-resonant antennas, when we make the ground plane small, the bandwidth is reduced. So we will see in the presentation techniques that we can use when we have small ground planes, but still we need to provide a lot of frequency bands of operation to our wireless device. So this is the dependence of the ground plane size versus bandwidth. And let me now illustrate what is the dependence of bandwidth with efficiency. So to sum up, for a rectangular ground plane, to maximize bandwidth, typically 0.4 lambda at the frequency of operation is the optimal one. And when the length is less than this maximum, or it becomes less than the lambda over pi, it will be around 0.3, then we have problems of bandwidth. Let's see what happens with efficiency. In this, I illustrate the ground plane length for an antenna booster at the frequency of 900. So for 40 millimeter to 120 millimeter, using the same width. In this case, the width is 60 millimeter. And we measure the efficiency. These circles are measures of efficiency at the frequency of 900. You can see that as we decrease the size, the length of the ground plane, the efficiency decreases. And this discontinuous line represents the boundary between small ground planes and big ground planes. As you can see, when we are in the region of big ground planes, the efficiencies we can get are 70 and above. But when we are in the region of small ground planes, the more we are at the left of this chart, the less efficiency we can get. The same happens with the pink line. However, the pink line is measured at the frequency of 2.2. So this boundary starts to happen at 40 millimeters. So you have to go less in size to have a small ground plane. So here it's a simple question. Imagine that we have a ground plane that is 80 by 60 millimeter, where the efficiency will be typically higher, at the frequency of 900 or at the frequency of 1800. So exactly at the frequency of 1800, the device will be electrically larger, and in 900 will be electrically smaller. So typically the challenges when designing wireless devices are at the lowest frequency of operation because the electrical size is small. Okay, now let me briefly explain why an antenna booster being so small can excite currents and how the position of an antenna booster matters in order to excite the currents on the ground plane. So in order to do that, I'm going to use the so-called characteristic mode theory. In brief, the modal significance obtained through this theory, it's a scalar number between 0 and 1 that tell us how good a mode can be excited. For instance, this is the first 4 modes for a ground plane of 120 by 50 millimeter. Let's imagine we focus with in the blue line. The blue line represents the characteristic mode for the first mode, for the fundamental mode. So this means that below 1 gig, it's difficult to excite this mode, especially at the frequency of 0.5 gig. The modal significance is only 0.1. This means that if we want to integrate, to embed an antenna booster in this ground plane, it's going to be difficult because the size of the ground plane is small. As we increase the size, for instance, this particular fundamental mode, well, at the frequency of 0.9, eventually the modal significance is getting larger. So it means that in some way we can excite this mode. The question is, okay, we know that this fundamental mode exists for this ground plane. How we can excite the first mode, the mode number 1 for this ground plane? Let's find out. In this experiment, it's a numerical experiment, we have a tiny antenna booster, only 5 by 5 by 5. In this case, it's a metallic cuboid with an RF probe that connects the antenna booster to the ground plane in green. The ground plane, in this case, is 100 millimeter by 40 millimeter. In one case, we have the antenna booster at the corner. And in another case, we have the antenna booster at the edge in the center. And we simulate the input impedance, real part and imaginary part, and with these equations, we compute the bandwidth we can get. Okay, and this is represented with the blue line and with the green line. And as you can see, at the low bands between, well, around 1 gig, the bandwidth we can get for the antenna booster at the corner is 20%. However, for the antenna booster at the center of the long edge is less than more or less 2%. So why? Is the same ground plane, is the same antenna booster. The only difference is the position. And the fundamental mode is there because it's the frequency of 1 gig. The answer we have at the right. The fundamental mode 1, it has an electrical distribution with a maximum at the corners of the ground plane, which is represented with this red line. It's maximum at the corners, and it has a minimum at the center of this long edge. That's the reason why if we put an antenna booster, which can be seen as a voltage source, if we put at the corner, we are going to excite this electrical field distribution. And as a result, we are going to have bandwidth. But if we put the antenna booster where we have a minimum of electrical field, we are hardly having bandwidth. This is the same as pushing the acoustic drum with the drumstick not at the boundary, but at the, sorry, not at the center, but at the boundary. The boundary, there is no pressure. So in this case, you can see what is the implication. So this means that the antenna booster position matters, and depending on the position, you can excite more or less the mode. Now, if we go up in frequency, now we can obtain, well, 40% bandwidth, which can be good, more than enough for certain kind of application. Why is that? Because now, in this case, we are exciting other modes. For instance, the mode number 4, it has a different current distribution, so a different electrical field distribution. In this case, there is a maximum of electrical field distribution at the center. So in this case, we can excite, and we can, in this case, we can have bandwidth that can be enough for our application. So in summary, the position of the antenna booster on the PCB matters to effectively excite currents and obtain bandwidth and efficiency. So if we do that, for instance, in this case, we have our ground plane, we have our antenna booster, we excite our antenna booster with an RF probe, you can see that the fundamental mode, typically in this case, it's aligned, the currents, the vector currents are aligned with the longest dimension, okay? And as a result, the radiation efficiency, it's quite high. It's about 90%. And we are only using an antenna booster that in terms of lambda is lambda over 50, okay? So the antenna booster is not the antenna per se. What is the antenna per se is the ground plane, which is about 0.3, 0.35 lambda. It's comparable to lambda, okay? So that's the meaning of the antenna booster boosting currents on the ground plane, okay? Now we are going to deal with input impedance. Input impedance is non-resonant. Let me just focus to this example. These are real wireless devices for IoT, Internet of Things kind of applications, and the red components are commercial antenna booster chips. And as you can see, mainly the feeding line goes at the corner of the ground plane. You can see here, and as a rule of thumb, in order to better excite currents on the ground plane, we should allocate the chip component at the corner of the ground plane to better use the ground plane. Other positions may work as well, okay? So now that we have understood the role of the position of the booster and the efficiency we can get, the question, or the second question we need to solve is, okay, what happens with the impedance? In this case, we have an antenna booster, very small. It's lambda over 30 at the frequency of 900. And we have some patch with 0 ohm resistors and a 50 ohm microcoaxial transmission line on a big ground plane. So imagine that we measure the input impedance, and we plot in the Smith chart. And as you can see, for instance, in the low frequency region, this is not much. This is very far away from the center, typically being 50 ohm. as a reference, most of the transceivers, they have 50 ohm reference impedance. So this is totally mismatched. The question here is what we can do if we want to change this input impedance, which is highly reactive, capacitive, to go close to the center of the Smith chart. And even more challenging, what if we need to operate for multi-band application, so low bands of cellular application, 5Gs in the low bands and high bands, and also at the same time we want to match all this frequency range. So how we can put all this frequency region and all this frequency region at the center of the Smith chart. So the reason is with a matching network. So the matching network will be placed between the antenna booster system and our transceiver, which is represented by this simple circuit. So at the end, the mission of the matching network, which can be inductor and capacitor, as well as other active components, as I'm going to illustrate right now, the mission of the matching network is to capture all the blue power, all the available power, to minimize reflection due to the reactance of the antenna booster, because the matching network cancels that reactance out. So we minimize, we have a good S11, and all the power enters the antenna system. And if the matching network has low losses, eventually the blue power will be the radiated power. So this is the mission of the matching network. And so let me put a very simple example. Imagine we have an antenna booster, lambda over 30, at the corner of the ground plane. The green represents substrate, typically FR4 for most of the wireless devices. Yellow is the ground plane, a big ground plane. And we measure or we simulate the input impedance. We put an RF probe and we compute the input impedance at 900 megas, 1 and 2, for instance. Highly reactive, so the S11 is minus 0.5 dB, very poor match. This means that most of the power of the transceiver will be reflected. This is not going to be efficient. But if we put a very simple matching network, in this case only 2 or 3 components, we can convert 1 and 2 to be 3 and 4, very close to the 50 ohm, to the center of the Smith chart. And as a result, now you can see the S11 is below minus 12 dB. So this means that more than 90% of the power of the transceiver is delivered to the antenna system and eventually will be radiated into space, and the other way around. The power received by the device will be delivered to the transceiver. And this is very simple, because now by changing the matching network, we can operate at, let's say, 0.7 gig or GPS or Bluetooth, whatever. And also what happens if we need to make our matching network multiband? Well, this can be totally addressed through circuit simulation. There are available many microwave solvers from OpteniLab, Cadence, ADS, Attune, that based on the input impedance as a data, we can request the algorithm based on genetic algorithms and other optimization procedures, that the algorithm give us as a result the value, the topology of the inductors and capacitors using commercial values that we can put in our matching network to meet the specs, if it's either single band or if it's multi-band. And if there is no solution, the software will do what is best. I mean, you cannot expand the bandwidth as much as you want. There are some physical limitations due to both the Fano criteria. But at the end, what you know is that you can push a lot to the software, and the software will do the best to reach those targets. And if not, you will know that this is the best solution that you can get. Let me put some examples on how we can design wireless devices embedding antenna booster. In this first example, we have an antenna booster lambda over 30 on a ground plane, quite large, 120 by 60 millimeter. And in this case, with a very simple matching network, we have, this is measured data, we have the SWR versus frequency, and we have efficiency. With a very simple matching network of only 2 components, we can get an efficiency of 90% across the frequency band of low bands, more or less 800 to 960 megahertz. Now, by using the same device, the same antenna booster, but only changing the matching network, in this case 5-component matching network, we can have multi-band, dual band. So a first region, about 900 megas with an efficiency of 70-80%, and a second frequency region, shadow in gray color, from 1.7 up to 2.2 in blue color with efficiencies from 60 to 90%. And again, the topology and the values, we don't need to use very complex mathematical formulas. It's everything addressed by software. So fast and very simple. Now, another example. This is with 7 components. In the previous case, the bandwidth reaches 2.2 gig. In this case, you can see that we are expanding the bandwidth up to more or less 2.7 gig. So this means that by pushing the matching network to expand the bandwidth, we can have a first band and a second band for multi-band operation. In this case, can be for 4G kind of application in cellular bands. Also, let me give some just highlights. Now we are using an antenna booster either for single band or multi-band application. Also, we are working in multi-radio. Multi-radio means that, imagine we want to integrate in a simple booster several radios. So we have a transceiver that operates at, say, 900 LoRa kind of application, GPS on Wi-Fi, and we don't want to use 3 antenna booster because we perhaps need to use 3 corners of the PCB. We are working in only using 1 antenna booster with 3 highly decoupled ports to do more or less the same, or to a certain extent to do the same. So this is multi-radio because each sinusoid represents a different radio. This is an example. For instance, let me show the latest things that we are working. This is a real product for multi-radio application where we use antenna booster technology for 3 independent ports for cellular application, satellite, GPS, and so on, and also Bluetooth. For those working in MIMO, for instance, multi-band at cellular bands, this is another example. You can have more details in this paper, where in this case we illustrate the flexibility of having several boosters at the corner of the ground plane. In this case, 4 tiny boosters, land over 30, and highly decoupled. And as you can see that by designing a multi-band matching network, in this case, 5 components, we can have 4 similar responses, and the H11 typically less than -10, here is -8, but as you can see, since these boosters are very small, we can populate the PCB with many boosters. Now let me briefly discuss about the role of tunable components in the matching network. So far, we have been using inductors and capacitors. And the question is, well, can we expand the bandwidth by using more components in the matching network instead of 5 if we use 10 or 15? The answer is no. You cannot expand the inherent bandwidth of the antenna system by putting more components. This is the Bode-Fano criteria, that with a matching network, you can expand the bandwidth up to 4 times, which is, it's a lot, but you cannot expand more by putting more components. So the question here is, let's imagine my device is not big, it's small. We understood some slides ago that by having a small ground plane, the bandwidth we can get is limited. So what happens if by any reason I have to design a small wireless device, yet I have to operate at several frequency bands? What can I do if I cannot obtain the bandwidth with a passive matching network? The answer is by using tunable components in my matching network. Let me illustrate 2 cases. One case is with a DTC, which stands for digitally tunable capacitor, and the second one is for SPNT, single port and throw switches. In the first case, we are using an array of capacitors. This is a tiny component that when you drive some data into this chip, you can see how small it is, 1.4 millimeter. You can change a certain capacitor. Typically, it's more than 30 different values. So let me illustrate this example. In this example, we have a ground plane and we have an antenna booster at the corner of the ground plane with a matching network, some components, tiny components, SMD 0402. So these are very, very small, 1 millimeter in size. And this black component here is a digitally tunable capacitor. You see how small it is. On the other layer, we have the control lines to put this capacitor at the value we want. And this is represented, in this case, is a shunt capacitor that, depending on the value, what we can do is the following. Let's imagine that we are operating in one state, let's say 0, 0, and this is the measured efficiency represented by the purple line. So at the low bands, we have 70%, close to 70% at 900 megas, but if we go at 700, efficiency is only 5%. We cannot do more because the bandwidth is the best we can do, okay? So the question here is, well, what happens if I use in an intelligent way a DTC in my matching network? So I change the value of this capacitor. Now we can match, and you can see that now we can have a good or an acceptable efficiency close to 50% across this frequency band of 700 to 750. So this means that a tunable matching network can expand the bandwidth you can get for a passive matching network. Let me illustrate another example. And this is adopted in a real IoT reference design by the company Nordic Semiconductor, embedding an antenna booster component in red. And in this case, the challenge was quite high. We, in a small device, only 50 by 50 millimeter, so in terms of lambda, it's a small device because we need to operate at 700 megas. So we need to operate from 700 megas up to 960 megas, a first frequency region, in addition to a second frequency region from 1.7 gig up to 2.2 gig, and also GPS. So with a passive matching network, it was very difficult to obtain this bandwidth. Or we match at the frequency 700 to 750, or we match from 900 to 960, but we cannot cover all the frequency region. So what we did to obtain good bandwidth and good efficiency, we proposed, and this is the architecture that is in this device called Thingy91, this architecture. This architecture uses SPNT switches, so you can connect an input port to any of these outputs in the following way. Let's imagine the transceiver, which is this element here, in charge of transmitting and receiving information, wants to operate at the frequency of 698 to 748. So in this case, the transceiver sends some data, control data, to the switches, to this SPNT. So the input is connected to this output. So at this point, we have the antenna booster, which is non-resonant, and in this case, we have a simple matching network to provide 50 ohm, which is the same input 50 ohm that we have here. So as a result, there is no reflection, and all the power eventually goes to free space. What happened now is the transceiver, which is connected to the base station, needs to operate another frequency range. Well, the same. Now the transceiver sends some control data, the input is connected to this output, and this output to this input, and so on, and so on, and so on. So with very simple matching networks, we are matching certain bands to cover the whole frequency region. And moreover, since we have enough states, what we did is we have another port to receive the GPS. This tiny signal is GPS. We have a matching network. Then this signal is amplified by this low noise amplifier and enter the input of this transceiver, which is also for GPS. So you can see, let me illustrate in this slide how it works. Every single matching network here, the blue, the pink, the red, the brown, the yellow, and so on, obtains a good bandwidth in a small bandwidth, but you don't need to operate across all bandwidth at the same time. Or we operate at the blue bandwidth, or we operate at the pink. So what we do is, okay, let's try to cover with this tunable architecture all frequency regions. So especially, as I said before, the challenges to obtain bandwidth are always in the small or in the lowest frequency where the device is electrically small. So you can see that now we can obtain from 800, so from 700 to 960 megas, we can cover with 5 states the whole bandwidth. So to sum up, tunable solutions are very convenient. for small devices when it's a challenge to obtain bandwidth with a passive matching network. And in this slide, I want to illustrate the benefits of using a tunable solution compared to a passive. This is the small device I was showing you before, and in this case, the green line represents the efficiency, and the gray represents the efficiency for the passive solution. For the passive solution, okay, it's comparable to the green in this frequency region where the matching can be good match at this frequency region, but as we move to other frequency region, well, you can see the advantage is very, very high. In some channels, maybe even more than 20 dB. 20 dB, it's a lot. So this means that if we have more efficiency for the tunable solution, we can get more range and we can ensure more battery life for my wireless device. So I think I have still 5 minutes more. So let me conclude or going to the final slides. Just to highlight the kind of radiation patterns we can get with antenna boosters, since the ground plane is small in terms of lambda, 0.4 lambda, 0.5 lambda, the kind of radiation patterns we get are mainly omnidirectional radiation patterns, no matter the frequency we are working with. Also, the design of matching networks, it's totally addressed by software. We don't need a human being to design these matching networks. In this slide, I compare the performance of a matching network designed through artificial intelligence process to a human being. Not only we obtain less components by the artificial intelligence process, but also more efficient. So this means that in the future, wireless devices may be totally designed by robots, and then we will have more time either for, well, to relax or perhaps to do more sophisticated things, less things that require parametric or repetitive tasks. And let me briefly, well, I'm going to share these slides, but just let me highlight the advantage of antenna boosters to other techniques. To self-resonant antennas, not only the size matters, but the time it takes to design a self-resonant antennas. You need to design parasitic elements, several branches. Antenna booster is done. You can use the antenna booster. The CST models are available in our webpage and can provide data. So the only thing we need to design is a matching network, which is really, really fast. It's a matter of minutes. And also, antenna booster compared to FPC antennas, when the FPC, which stands for flexible printed circuit antenna, it's on the PCB, it's highly affected by the ground plane. In this case, I represent the efficiency for the same PCB antenna booster in red, compared to FPC, which is very, very big flexible antenna. You can see the efficiency in the low bands. It's very difficult to obtain high efficiency because the FPC, it's placed above the ground plane, so it's highly impacted. FPC are good when the FPC is off PCB, but when the FPC is on the PCB, it detunes a lot the performance, and in this case, the efficiency we can get, it's much less than the efficiency we can get of antenna booster. And let me conclude with the latest thing that we are working with that has to, sorry, let me close the door. Let me finalize this couple of minutes I have with the aim of connecting plants with plants with another plant, with the purpose of having our forest more resilient. I don't know if you are aware, but here in Spain, this summer, we have been suffering from a lot of wildfires. So it's really a mess. So if in somehow we as engineers can help and can make the plants can communicate one plant to another and to another and to another, just to share the status of I am burning, I'm thirsty, I need water, that we believe that this will help to make our forests more resilient. This is an European project with several partners, Ignition, also my university, Ramon Llull, with other partners, to bring connectivity and also to harvest energy from soil. So at the end, we don't need batteries. So the first proof of concepts that we have is that since we are going to use very small PCBs in the plants, because we don't want to have a big device on the plant, if we have a small PCB on the plant, as we already know right now, a small PCB means efficiency is going to be limited. In this case, you can see this small PCB with a tiny booster. Also, tiny booster, it's convenient for a small PCB. Efficiency in this case at the frequency of 900 is about 25%. It's not, it's poor, maybe enough, but when we somehow connect in this preliminary way to a aloe vera leaf, we can see that overall we can boost more efficiency and we can improve efficiency up to 3 dB. So here we are exploring in this research project how we can leverage from plants to make our antenna systems more efficient by combining antenna booster and plants. So you have some details in this paper that we published at the European Conference of Antennas and Propagation. If you cannot have it, let me know. I can share with you, because we have the first proof of concept with this direction. So I think, yeah. Let me conclude. Here are some real examples of wireless devices embedding antenna boosters. So we are happy that this technology was born from pure research. Research is very, very important to drive smart things. And now at the company, at Ignition, we are happy to bring connectivity to make our life easier and comfortable, and to bring connectivity even to forests, hopefully very soon. By the way, this is a Kavli wireless device from India, where we integrate this antenna booster. This is another device from India, from Rioche. Thank you to Rioche company for providing this detail, where we illustrate that by using the same antenna booster, we can provide performance to cellular, to GNSS satellite, and also to Bluetooth. The only thing we change from one booster to another booster is the matching network. So this is a very nice example that we don't need to use a different antenna booster. We can use the same antenna booster for any frequency band, and also for any form factor, by only changing the matching network and by properly placing the antenna booster close to the corners of the ground plane. So antenna boosters are very small components. They can be single band, multi-band, multi-radio. They are cheap components. So this means that they can be easily assembled into PCBs. So this ensures robust and high quality when building a million of these devices. And the kind of application goes for tracking devices, smart meters, for any kind of applications, between 400 mega up to 10 gig. I want to appreciate all the funding that we have received from the European Union, also for Spanish ministry. Also, I want to thank Dr. Mohit for inviting me. Also, all of you for your attendance. I hope the presentation has been interesting and practical. For those of you teaching, also students, if you go to Google and write down virtual antenna MOOC, this is an open course, 8 hours for free, plenty of materials that you can use for your teaching. And if you want to learn more, please use this open free course. Also, the book that we published last year, this is plenty of exercises. So if you are a professor and you want to have perhaps a crash course for some weeks, there are plenty of exercises for students and also for research. And a lot has been done in this topic, but a lot still can be done. So please use my email. It's typically my university email if you want to contact me and we can discuss anything. So with that, I conclude my presentation, and thank you very much.
Thank you very much, sir. Any queries from the participants? I invite it.
Hi,
Okay.
sir. I am Raghava from Andhra Pradesh, India. Excellent presentation, Professor. Please share how PDF opportunities in your university.
Sorry, I didn't get you. Can you repeat the question?
Postdoctoral fellow opportunities in your university.
Yeah. If for any, by the way, we have one researcher from India, Abed Siet. He's working with us in a Spanish research project. So yes, let me tell you, there are fundings for that will be open by the end of this year. So anyone having looking for a postdoc position, typically it's 2, 3, sometimes even 4 years. Please send me an email, and then I can put in contact with the person in charge, because there are some paperwork to do and to apply. This is something that you don't have for granted. You need to apply. But if you get those grants, then yes, there are open positions that we can apply for that. So use my email for that, please. Thank you.
Full-time or part-time, sir?
Sorry?
Full-time or part-time? Part-time,
you mean?
From here, from few months there.
Let me know what your ideas are, and we can explore. I mean, typically the funds we have now are for full time, and these researchers at ECE, it's in Spain for the last 1 year, and he will be with us at least 1 year and a half more. So I don't know if for part-time perhaps is still an option. Share with me the options you have in mind. I can explore with my university.
Any other queries?
I think there is one. Dr. Tech Rak has raised his hand. I don't know if he has a question. Dr. Tech Rak.
Please expand research area in this booster technology, antenna booster technology.
Sorry, that was a question? I couldn't.
Sir, he's asking about the research area in antenna booster technology.
Okay, so for instance, MIMO can be one, how to use, for instance, the coupling networks, because once you integrate many boosters in a wireless device, if you have the coupling, highly coupled elements, how you can decouple by using the coupling networks. Another topic will be continue exploring tunable solutions. Okay, there are other components in the market, other architectures that can be explored in the market. What else? Now we are exploring this green element with plants, so perhaps also exploring how we can leverage performance from plants. That can be also a topic that we are now working with that. So mainly these three kind of lines, perhaps also, I don't know, any new tool to optimize matching networks. This is quite mature. So the way matching networks are optimized, they are available in softwares, as I said. So I would say MIMO, tunability, perhaps wearable application, also to have boosters and to understand how robust these structures are in front of human bodies for kind of wearable applications can be also a good topic to do research.
Hello.
Okay. Yeah.
Good evening, sir. This is Mohammad Sarwar Rahim. I have one question to you. Sir, what are the opportunities in the energy harvesting by the green plants?
That can be also a good point. Yes, I think it's a good option because at the end, the only thing you need to match, well, it's not simple, but if it's energy harvesting, you need to have a matching network for matching to the rectifier. So I think it will be nice because those rectifiers, especially the input impedance is nonlinear. So depending on the input power, the input impedance of the rectifier, it's one impedance, but if the input power is higher, that so I think it's worth to explore. In the past, we did some exercise, but we are not doing that. So I think combining antenna boosters, matching networks combined with the rectifiers of energy harvesting system can be worth to do it.
Yes, sir. Thank you, sir. Sir, one more question I have to you.
Okay.
Which software I have to utilize for the designing the antenna for the base optimization? Sir,
Can you repeat at
told
the
about
beginning?
the
I lost
energy
you.
booster. Yeah, I am talking
Sorry?
about the energy boosters. I am talking about the energy boosters. For the energy booster designing by the software, which software is most
Okay.
powerful?
Yeah.
Yeah.
Antenna boosters are available in the web page if you want, and they are open. It's typically CST. There are models that you can use for your own simulation. If you send me an email, I can show you where these models are in the web page. You can download and you can use the model for doing your research. Typically, CST Microwave Studio, and HFS from ANSYS. It's good electromagnetic simulation. This is for modeling the input impedance of the antenna booster on your wireless device. Once you have your input impedance and you want to design the matching network, it's true that this software, CST, HFSS, and so on, they have also the possibility of putting components, but there are, to me, more powerful circuit simulators, which is OpteniLab. You can Google it, OpteniLab, and if not, send me an email, I can provide. Attune, which this is a very powerful simulator, because once you put the input impedance, they give you, as a result, the topology of the matching network, which is great. It's 5 components, 6 components, 7 components. I want to match at this frequency region and this frequency region. Give me the topology, give me the values I need. 4, 5, I don't care. I don't need to use complex equations. So, wow, this is great. So those software for input impedance simulation, OpteniLab, Attune, are very powerful. And for full wave simulation, CST, HFSS, even FECO are very powerful. And also there are other softwares that can be also used as well. But if you want to use models, we already have some models that you can download for free in the web page and that you can use for your own purpose.
Thank you, sir. Thank you very much, sir.
You're welcome.
Any other queries? Sir, I have one small query. Can we use the antenna booster technology in millimeter wave band?
Yes. The only thing is, imagine that we go up in frequency to 30 gig. Okay, let's put that example, 30 gig.
Yes.
And a 30 gig microstrip patch, lambda over 2, it's about 5 millimeter, more or less. So size of 5 millimeter for an antenna perhaps is not that critical. Okay. So, but I don't want to discourage. As long as at the end, as we see, 3 ingredients: antenna booster, matching network, and ground plane. So if the ground plane for the millimeter wave is not big, it's a small internal of lambda, then you are going to suffer bandwidth limitation. So to me, working at that frequency, typically ground planes are big. And I'm quite a bit reluctant to see this technology. We can use it, but compared to a microstrip patch, perhaps microstrip patch can do a very good work because it's still very, very small. So I don't see at this level how this technology can shine for those frequencies. It's worth to explore, but I see more challenges.
Thank you, sir. So one small question is that in your country, there is any fabrication facilities for terahertz frequencies?
For terahertz?
above 100 gigahertz.
You mean at the company level?
At the company or at the institute level, sir?
At the company, typically the frequency range we are working it's for IoT, so it's below 10 gigahertz, or 600 megas up to 10 gigahertz.
Thank you, sir. So many researchers want to know that if they want to research in your country for the postdoc and fellowship. So
Send me an email because now is the right moment. As I said before, they will be open funds to apply by the end of the year. So please send me an email and I can put in contact with the right person to understand the paperwork that has to be done.
Thank you, sir. Any other queries from other participants? Thank you, sir. I would like to thank you, Dr. Jome, from the bottom of my heart. He shared the valuable insight on the antenna booster technology. I believe that participants will gain valuable knowledge from his session. Thank you very much, sir.
Thank you to all of you, and I will share my slides in case you want to share. There are plenty of reference. My email there, if anyone want to contact. So
can you share your PDF means or PPT with me?
Sorry?
Can you share your PPTs means participants are asking your presentation PPT. Can you give me your presentation PPT on my mail?
Yes. I will share the presentation to you, and you can share with all students. Okay.
Thank you, sir. Thank you, sir.
Yeah.
Thank you very much.
It has been a pleasure. So from today, I'm in my hometown, close to Barcelona, a small city close to the beach. So it has been a pleasure to talk with all of you. I wish you a good success in these 5-day antenna-related courses. And you can contact me anytime, or if you belong to another university, please, you can reach me if you want me to deliver also a talk. It has been a really pleasure. So, Dhanyavad.
Thank you, sir. Namaskar, sir. Good night. All participants, you can fill the feedback form. Please fill the feedback form for session 1 and 2. I have also shared the feedback form in WhatsApp group. And please note that the attendance will be taken by the Google Workspace software automatically. Login and logout time will be noted by the software itself. After submitting the feedback, you can leave the meeting. अरे सर से बात करो ना, क्या बोल रहे हैं?